Anybody know any burrito jokes? Where's Marcus? That's a good one. Okay. Example 7. All right. It says find the solutions to. So these now are conditional equations. They're only true in certain conditions, and we solve conditional equations to find those conditions or values of x, in this case, for which they're true. So find the solutions to 2 sine squared of x plus sine of x equals 1, such that our solutions are between 0 and 2 pi, part B from 0 to 4 pi, and then from negative infinity to infinity. That's a pretty big interval. So first things first, we're going to stay in our comfort zone. Within one positive rotation on the unit circle, are there any values of x that make this thing true? Well, we shall see. 2 sine squared plus sine of x equals 1. Does that resemble anything that y'all might have seen in another math class, like Algebra 2? Minus the sins in there. It looks like a quadratic, right? It looks a lot like 2x squared plus x equals 1. And it is. It's exactly what it is. It's a quadratic equation, but it's in terms of sine of x instead of x. So you can use really the same techniques. What would you do if it were 2x squared plus x equals 1? If this were what you were having to solve, what would you do? You would set it equal to 0, right? When you have a squared term, a non-squared term, and a constant, your goal is to set it equal to 0 so that you could what? Factor it. Good. So let's do that. So 2 sine squared plus sine of x, and now minus 1 equals 0. And so this is going to factor, if it does factor, fingers crossed, into the product of 2 binomials. If it doesn't factor, we always have the quadratic formula, which we could still use, but our solutions would be equal to sine of x, not x. All right, so remember to factor. We're looking for factors of 2 that add up to 2 and 1, that add up to 1. So 2 is prime. So this has to be, instead of a 2x, it has to be a 2 sine of x, and that has to be a 1 sine of x. Now, you already know that that's going to work, because if you multiply those first, like in foiling, you get 2 sine squared. The last number back here is a 1. That makes it really nice, because there's only one way to factor a 1, and that's a 1 and a 1. So when you do the L in the FOIL, 1 times 1 is 1. Now you just got to make sure that the signs work out. I want to end up with a negative 1 product and a positive 1 sum. So to end up with a negative 1 product, the signs have to be opposite. And to end up with a positive sum, the larger product has to be positive. So the larger product is going to be the outside. That's 2 times 1. And then the inside product has to be the smaller one. So that's a minus. So that's how you factor, right? We're just doing it with sine of x's instead of regular old x's. So you'll get used to factoring quadratics. Okay, sweet. So now that we have it factored, what was the next step? You set them equal to 0. Good. So you got 2 sine of x minus 1 equals 0, or the other solution would be sine of x plus 1 equals 0. And now you would solve for x normally, but now we're solving for sine of x. So you add 1 and divide by 2. You get sine of x is equal to a half, or sine of x equals to negative 1. We were solving equations almost identical to this recently in BC Calculus. Eric can attest to that. When we're finding polar area, we need to find polar zeros. So we set trig equations equal to 0, and we solve them from the unit circle. So this skill right here, very important. You'll see it again if you go on to take more math. All right, so now it's unit circle time. All right, I could take the inverse sine of both sides, but I don't want inverse sine the function. I want inverse sine the operation. I want to know what all the angles are, x, within one rotation where the sine is equal to positive a half. So where is sine equal to positive 1/2? The one in the PVR would be pi 6. But we want all of them between 0 and 2 pi, so where's the other one? 5 pi 6. Very good. Quadrants 1 and 2. And we do the same thing over here. Where is sine equal to negative 1? Within one positive rotation, not the PVR anymore. 3 pi halves. Good. So that's the difference between inverse sine the function and inverse sine the operation that we do to solve equations. So those are your 3 solutions between 0 and 2 pi. Yay. Okay. We didn't really use an identity on that one, but we did factor, and we did use the unit circle. Okay, so now part B. I want to find all the solutions between 0 and 4 pi. Well, are all three of these solutions going to still be solutions then? Yes. And then I want all the ones that are one more rotation away, which means the other three solutions are going to be what to these? Coterminal, right? So let's go ahead and list them. Let's list them as coterminal buddies. We got x equals pi 6, and his coterminal buddy, one rotation away. $13 pi 6. Dang. You're like an Asian wok back there, just sizzling hot. Okay, yeah. You had a full rotation, 12 pi 6. You get 13 pi 6. Then you get 5 pi 6, and his coterminal buddy. Who? What did you say? 17. Yeah, 17. I just didn't hear it. Yeah. You could be an Asian wok as well if you want, Philip. There's plenty of those to go around. Every Panda Express has a couple of them. And then 3 pi halves and his coterminal friend. 7 pi halves. Good. So this time when we had 2 pi, we had 4 pi halves. So those are all the solutions between 0 and 4 pi, which is 2 rotations. All right, now part C. We want to find all of them. How many solutions are there? Infinity times 3, right? Because each of those 3 has infinitely many coterminal angles. What's infinity times 3? Infinity, right? That's a lot. So we are not going to list all of them. We're going to do kind of the same thing we did when we were listing where vertical asymptotes were, which were infinitely many. We're going to find our first one and then multiples of how often they occur. So that's a real easy thing to do. So on part C, the solutions are, let's take the ones that we found at first, the ones that we like that are close to home. Pi 6 plus all of its coterminal buddies, which are multiples of what? 2 pi. So 2 pi n, where n is a what? A integer, yeah. And then 5 pi 6 and all his coterminal buddies plus 2 pi n, where n is an integer. Now people sometimes invariably ask, can we subtract 2 pi? I'm like, yeah, we can. N is an integer, so n could equal -1. And when n is -1, we're subtracting 2 pi. When n is -2, we're subtracting 2 rotations. So even though we're saying plus, it takes care of the subtraction. And of course, when n is 0, we get the actual values. And then the other guy, 3 pi halves, and all his homies, plus 2 pi n, where n is an integer. So that's what we would do if we had to list all of them. We're not going to list them all, but we're going to create little equations so that those people who want to know what the other solutions are can generate them on their own time, right? Until their heart is content. All right, very cool. Any comments or questions on example 7? Solving equations, right? Feels good to be a problem solver. You're contributing to the world, right? You're not part of the problem. You're part of the solution. Yeah. And if you're not part of the solution, you could be part of the precipitate. Yeah. All right, example 8. Find the solutions to this. Whoa. Cosine cubed of x over sine of x. That one looks a little more fun. So that all of our solutions now are between -2 pi and 2 pi. And it says, be careful not to lose any variable information in the process, like cotangent of x. Make sure your final answers are in the domain. Okay, I got it. All right. You need all the warnings. Figure it out. All right, what should we do? Cross out the 3. Put it in terms of sine and cosine. That works. Okay. So we got cosine cubed of x over sine of x. That's already in terms of there. Would you want to bring the cotangent across as well? Maybe not. Equals cosine of x over sine of x. Now, one of those sines divides out from both sides, and one of those cosine divides out from both sides. In other words, a cotangent divides out from both sides. Do we want to do that? Be careful not to lose any information like a cotangent. Uh-oh. That's exactly what they was warning us against. Why do we not want to lose a cotangent of x from the equation? Ask a silly question, get a silly answer. Yeah. No, if you ever lose variable information from a conditional equation, you lose possible solutions. Did you hear that? When you lose variable information from a conditional equation, you lose possible solutions. So we don't want to divide those things out. So it's okay to put everything in terms of sine and cosine, but because they have variables in them and they don't reappear, you know, sometimes if you multiply both sides times sine, it can reappear. You don't want to do that. So instead, let's bring everything across and we'll set it equal to 0. Okay. Yeah. And now we can get a common denominator. We have a common denominator. So I got cosine cubed of x minus cosine of x all over sine of x equaling 0. Now, here is a very important part. If you multiply both sides times sine of x, it's going to divide out on the left, and it's going to be gone on the right because anything times 0 is 0. So you don't want to do that, right? Because now you're losing sine from the equation. That would just leave us with cosine cubed minus cosine. But we're going to get the same result, but by a very different mentality. When you have a single fraction and it's equal to 0, a fraction is equal to 0 when the what is 0? Numerator or denominator? When the numerator is 0. So this single fraction is equal to 0 when the numerator, cosine cubed minus cosine of x, equals 0. So we're still ending up with the cosine cubed minus cosine equal to 0, but we're not getting to that line by multiplying both sides times sine. You got it? We're still considering the highlighted equation as part of the equation. Well, now I have cosine cubed minus cosine. I can either factor out an x, like Thornhill suggested so humorously yesterday, or factor out a cosine of x, which is better. That leaves us cosine squared minus 1. And by the way, once something is equal to 0, that's your goal, to factor it. And now that it's factored, we can set each factor equal to 0. So cosine equals 0, or cosine squared minus 1 equals 0. And now it's unit circle time. Where does cosine equal to 0? All of them. Pi halves, that would be in the PVR, but we want all of them. 3 pi halves. So those are the two between 0 and 2 pi. We want the solutions from negative 2 pi to 2 pi. So we need the coterminal buddies with these guys that are one rotation backwards. So what's pi halves minus a full rotation? Negative pi halves, and 3 pi halves would be negative 3 pi halves. So those are the 4 solutions from that guy. Now we got to be careful. Remember up here we had sine of x in the bottom? What happens if one of those gives us division by 0? It's undefined. We have to toss it out. Do any of these solutions make sine of x 0? No. Sine is equal to 0 at 0, pi, 2 pi, 3 pi, multiples of pi. All right, let's finish it up here. If we add 1 to both sides, we get cosine squared equals 1. When I take the square root of both sides, we have to consider both what? Positive and negative. So it's equal to negative 1 or positive 1. So now it's unit circle time. Where is cosine equal to negative 1? At pi, or one rotation away, negative pi. And where is cosine equal to positive 1? 0, 2 pi, and negative 2 pi. But remember, we never got rid of the sign up here. We only set the numerator equal to 0. Do any of those solutions make sine of x 0? Yes, which ones? All of them. So they can't get into the club because they tear the club apart. Okay? They cause division by 0. So they are not in the domain of the equation. They cause division by 0. So the only solutions are those. All right? That is how you solve a trigonometric equation. All right, tomorrow we'll pick up with example 9. Make sure you memorize your identities if you haven't already, and then start your worksheet if you haven't, okay? Help yourself, help yourself. And then again, if you forgot the retest this morning,